To most people, this probably looks like a strange map of planet Earth. It is in fact compelling evidence of the Big Bang. But how do we know that this was how our universe began? Keep watching to find out. In Holden Township in New Jersey of 1964, two radio astronomers, Robert Wilson and Arno Penzias, were experimenting with the Holmdel horn antenna. As they were analysing their data and drinking coffee, they realised they'd stumbled upon something pivotal that had never been seen before. Wow, this data is definitely different. It looks like there's a background noise that I can't account for. I already checked it isn't interference from the city. Probably a bird nesting in the antenna horn or something. I'll go take a look. But when Penzias looked in the machine, there was nothing there apart from bird droppings and dust. No, there's nothing in there. This looks like it could be a new discovery. So the data's real? We need to document this. Fast forward to the 18th of November 1989, and excited about what the data could reveal about our early universe, NASA launched a Delta II rocket containing the Cosmic Background Explorer telescope. This telescope was the first of 3 space-based instruments that would eventually be used to measure and plot an image of the cosmic microwave background. The telescope cost NASA a cool $160 million US. That's nearly 400 million in today's money. The data on the cosmic web background allowed us to confirm the theory of the Big Bang, and some 14 years after Wilson and Penzias discovered it, they were awarded the famous Nobel Peace Prize. The average temperature of the CMB, and indeed space itself, has been shown to be around 2.7 Kelvin, which in normal English equates to about minus 270 degrees Celsius or minus 450 degrees Fahrenheit. That's pretty cold. If you were to be exposed to it, you would freeze to death pretty much instantly. More recently, the Wilkinson Microwave Probe, a NASA spacecraft operating over 9 years, has helped us learn that the universe is mostly dark energy, dark matter, and a very small amount of normal matter, the stuff that you and I and the stars are made of. The discovery of the cosmic microwave background is an important one for science, as it allows us to investigate our early universe. In our introductory episode, we looked into the first ever miraculous event, the Big Bang. But what was it like after? Well, despite a lot of heat, light and energy, the early universe spent the first 375,000 years cooling and doing very little else. This was the period when the CMB had become visible, but was ironically nicknamed the Dark Ages. Somewhere between 100 million to 400 million years after the Big Bang, the helium and hydrogen that was initially created began to gather together to form pockets of more dense gases that swirled and mixed. These denser areas eventually got so massive that gravity began pulling the gases closer and closer together. The pockets became so dense and under such high pressure, they ignited in gigantic fireballs of thermonuclear energy. Now, it's really crucial for the first stages of the creation of life at this point to mention that something very interesting and important is happening in these fireball explosions. It's easy to assume that these fireballs ignite, then expand, and then spread out until all the fuel is used up and the explosions disappear. However, because there is so much gas all clumped together, the weight, pressure, and gravity of its own mass prevents the explosion from continually expanding into space. It becomes a huge balancing act that occurs completely naturally. Pressure and power pushing outwards, and gravity pulling inwards. The intense pressure creating heat well into the millions of degrees Celsius, but the immense gravity of the mass itself pulling it all to the centre, maintaining the pressure. It's a stable cycle called hydrostatic equilibrium. And it's hydrostatic equilibrium that creates stars. And that's exactly what began to appear. And there were trillions of them. These stars differed significantly from the stars we observe today. Their immense mass, hundreds of times that of our Sun, made them incredibly luminous and scorchingly hot. The extreme heat and pressure at their cores triggered thermonuclear fusion reactions at an astonishing rate, resulting in an intense release of energy in the form of light and heat. However, due to their enormous mass, the first stars had relatively short lifespans, often only a few million years. This was in stark contrast to the billions of years that smaller stars like our Sun can live. The high mass of the first stars led to rapid depletion of their nuclear fuel, hastening their inevitable fate. When the nuclear fuel was exhausted, the core of these massive stars collapsed under the influence of gravity. This collapse generated an intense shockwave that propagated outward, resulting in a catastrophic explosion known as a supernova. The energy released in this explosion was so immense that it briefly outshone entire galaxies and could be visible across vast cosmic distances. The violent supernova explosions not only signalled the end of the first stars' lives, but also played a pivotal role in shaping the cosmos. These explosions dispersed heavy elements forged within the cores of the stars throughout space. Elements like carbon, oxygen and iron, crucial for the formation of planets, were spread far and wide, eventually becoming part of the building blocks for subsequent generations of stars, planetary systems and even life itself. Furthermore, the remnants of these massive stars took on new forms. Depending on the mass of the original star, the remnant could be a neutron star or even collapse into an incredibly dense black hole, bending the fabric of space and time itself. In essence, the first stars in the universe were the cosmic trailblazers that set the stage for the complex universe we observe today. Their birth, evolution, and explosive deaths enriched the cosmos with the ingredients necessary for the formation of galaxies, stars, and planets. As we gaze into the night sky, we're not only witnessing the beauty of the universe, but also the enduring legacy of those ancient and brilliant luminaries. And so, the birth of stars is the second miraculous event after the Big Bang hitting the #1 spot. Hydrogen and helium formed stars and were balanced by physics under a hydrostatic equilibrium. It may sound dramatic, but without these first events, or if the laws of physics were off by only a tiny % of what we see, we would very likely not exist. This is truly where life really came from, the origins of it all. Like and subscribe, and leave us a question in the comments. We'd love to hear from you. See you soon.